Hi, we are Team Virtual Reality Clinical Immersion for 2023's UCI Master of Engineering Capstone Project. Our team is made up of Veronica Romo, Yue Shui, Zhuan Yu, our team lead, Shujing Huang, Professor Christine King, our faculty mentor, Dalton Salvo, Dr. King's PhD candidate, and Professor Farzad Ahmed Kenelu, our advisor. Following and observing skilled physicians in real-life clinical scenarios is a critical component of a medical professional's training. Unfortunately, training hospitals are often limited in size and accessible only by students at selective medical schools. Virtual reality, or VR, based clinical shadowing would give the essential experiences to a broader population of students in a wider variety of settings. Dr. King's lab at UCI brought our team up to speed on their project, covering experiments related to quantifying boredom, an essential aspect of validating user engagement in VR immersive experiences. Our team's responsibility was to further enhance boredom quantification by implementing an accessible eye tracking feature compatible with a webcam. In order to quantify boredom, the two primary sources used were EEG and eye tracking. The EEG allows us to see where and when the brain is active, which directly correlates to if the subject is in a state of boredom or excitement. On the other hand, eye tracking also gives data that can indicate a state of boredom, such as persistent blinking, eyes completely closed due to falling asleep, and consistent shifts in the subject's gaze. In the experimental setup, the EEG cap was connected to the EEG bioamplifiers, enabling the EEG data to be acquired and saved onto the PC. This data was then processed via a MATLAB code. In contrast, eye tracking for boredom quantification for our project involved utilizing a standard webcam and running a C++ code, which collected data via the frames of the video and pupil detection. The eye tracking data was then produced and stored and later processed via a MATLAB code.
General input first, this code will capture the frame from the user's webcam. Then the code will identify facial features. At the beginning of our code, we will cascade classifiers for face and eye identification. In the meantime, we will initialize detect parameters that help us to precisely locate the eye and the center of eyes. After that, we read frames from the user's webcam. Then the face cascades classifiers is employed to detect faces. Next, we use the detect parameters to select the eye regions on the face. Using an eye cascade classifier, we can accurately detect the user's eyes within the selected face region. Now comes the crucial step: determine the precise location of the eye centers. We employ a series of functions and algorithms, including gradient calculations and Bayesian plot filling. In this way, we can accurately find the eye center localization. Here, we let a team member to watch a video and use our code to track her eye movements. Then we plot these movements using the MATLAB. Here are the three videos: the sample video, the recording of team members' eye movements, and the MATLAB plot illustration. As observed, our code demonstrates a relatively high level of accuracy in detecting and tracking eyes. However, to establish a measurable standard for accuracy, let's move to the next section, where we will conduct results and data analysis.
First, to simulate the scenario of students' gaze positions while watching a screen, we created a video tracking the focal point of a student's gaze. During testing, we collected eye tracking data using both our developer software and a professional headset with built-in eye tracking functionality. We used the data from the headset as the benchmark and compared it with our data to measure accuracy. We processed the collected data files in MATLAB, plotted their trajectories on the same window, calculate the mean square error at each time point, and finally determine the overall accuracy based on predefined thresholds. This figure represents the process of handling data from two sources in MATLAB. Through normalization and interpolation, we synchronized the two sets of data in terms of time and then proceeded them to compile and calculate.
The graph shows the curves of the two datasets in the y direction. As output in MATLAB, the orange line represents the actual values, while the blue line represents our output results. It's evident that in this video segment involving vertical eye movement, our data demonstrates a high level of accuracy. The following two graphs depict simulation conducted in different scenarios, along with the accuracy and the cross correlation coefficient calculations. We tested accuracy and correlation coefficients for various scenarios, including students wearing or not wearing glasses, different viewing distances, and varying lighting conditions. In weeks 1 to 5, the project focused on establishing requirements, creating a Gantt chart, and conducting background research on boredom changes and the data acquisition process. Webcam eye tracking was introduced during this period. In weeks 6 to 10, the team implemented webcam-based face and eye tracking, conducting preliminary experiments to validate the technology. Weeks 11 to 16 involves the concluding code refinement, developing standard operating procedures, and processing and validating the test data. Finally, in weeks 17 to 20, efforts were directed towards attempting to integrate the eye tracking function in the project. And thank you for listening to our presentation of our capstone project.